So today, we're going to continue on with what we left off with yesterday. So quick review. Yesterday, we went over kind of the conventions around adding vectors. Right? We said that when we're drawing vectors, we always draw vectors as an arrow. The length of the arrow represents the magnitude of that vector, and the direction the arrow is pointing represents the direction that the vector is supposed to be going. Okay, so that's one of the things we have to remember. Whenever we have to add vectors, that is, put more than one of them together, we always put them together in what way? Tail to head. All right, so I draw the first vector, and then I put the tail of the second vector on the head of that one, kind of like telling a story. This happened, then that happened, and then this happened. Okay, and we put it all together like that. So we looked at a few examples of that yesterday. We got to solving some to do with perpendicular vectors, where we had to do some Pythagorean theorem and some trigonometry and stuff like that. And then at the end of the day, I put one up that was like pretty far along in terms of where we're going with vector component addition. And that's what I'm going to kind of draw on here next, is something like what we left off with, okay, to illustrate why we use vector components to solve vector addition problems. Okay, so what I would like you guys to do is kind of draw this same picture that I'm going to draw as an example here. Okay, so that's kind of what we left off with yesterday. I drew these two angled vectors. And I said, all right, we need to figure out, since they're both displacement vectors, what the total displacement over the entire trip is going to be equal to. Okay? Remembering, of course, that displacement is our complete change in position, okay, over the trip. So the trip starts here at my initial position. And then the object travels 10 meters at 50 degrees south of east. Okay, how do I know it's south of east? Well, in case I'm directionally challenged, which I'm not, okay, but if I was, okay, I would look at a compass and go, all right, this arrow is pointing southeast, and the angle is drawn from east, moving south of east. Right, so I know that 50-degree angle is 50 degrees south of east. Right? After that 10 meters, the object turns, and it now travels 8.0 meters at 30 degrees north of east. And again, I know this is north of east because the angle arc is touching east and moving north of it. Okay, so it does that for 8 meters until it arrives at its final position, right there. So where would I draw a line that represents the total displacement over the whole trip?
From the initial position to the final position.
Right, from the initial position to the final position. Okay, like that. That line represents the total displacement of this object. So what we need to understand about this trip is that during this trip, the object overall travels south and east. Okay, everyone okay with that? All right. This line here would represent the eastern or easterly component of its motion. That line is how far it goes in total east over the whole trip. trip. Everyone okay with that? Okay. Because that line is horizontal, we call it the x component. X-axis, x is horizontal. Okay. This line here represents how far south the object goes over the whole trip. Because that line is vertical, that's the object's total y component. Now, each part of that trip also has an x and a y component. Okay? If I want to calculate what my displacement is, not only do I need to know how long this line is, I also need to know what direction it's pointing. And if I'm going to know that, I need to know at least two things about that green triangle. I've got to know two sides, or a side and an angle, okay? Or two angles, but we won't do that. Okay, we'll either go two sides or an angle and a side. Okay? In this case, we're probably going to find two sides. Right? And the reason we're going to find two sides is because I have information about the other two parts of the trip that can help me figure out how far east they went while they were doing this, and how far east they went while they were doing this, and also how far north they went and south they went during each part. Okay? That is, I'm going to find the vector components of each one of those vector quantities. Okay, so that's the language that we'll be using. These are x and y are vector components. They're the horizontal and vertical components or parts of each vector. All right, in this black triangle, I know that the hypotenuse of that triangle is 10 meters long. And I have a 50-degree angle there. With that information, can I figure out the other two sides of that triangle?
Are you allowed to assume that like that angle is a 90? 'Cause, like,
Oh yes, definitely. These are all right angles.
Okay.
Yeah. Sorry, I shouldn't draw that in green, that'll be confusing. But yes, I only drew right angle triangles on here. Okay, so how would I calculate the other two sides? For that black triangle, I know the hypotenuse and I know the angle. Right? That means I can find the opposite side and adjacent side using cos and sine. Okay? Because I have the hypotenuse and I have an angle within the triangle. Right? So if I can remember from last year in math, okay, that the sine of theta equals the opposite side divided by the hypotenuse, okay, or that cos of theta equals the adjacent side divided by the hypotenuse, okay, or that the tan of theta equals the opposite side divided by the adjacent side, okay, I'm good. So, which one of those trig functions could I use right now to solve for black x?
Cos?
Cos. Okay? And the reason I would use cos is x is adjacent to the angle that I have. Okay? The angle that I have here is touching that side. It's beside it, adjacent to it. Okay? And I have the hypotenuse. Right? So I have opposite and I'm looking for adjacent. Sorry, I have hypotenuse and I'm looking for adjacent. Okay? So I'm going to use this formula here, knowing I know theta and hypotenuse, I'm going to solve for adjacent. So what do I have to do with hypotenuse to get adjacent by itself?
Multiply it on both sides.
Right, just going to multiply it over to the other side. Simple algebra, right? I'm dividing by hypotenuse. If I want to move it, I got to do the opposite. So I can solve for black x by simply going the cos of 50 degrees, okay, my angle there, times the hypotenuse, 10 meters. Okay, so make sure your calculator's in degree mode when you're doing this, by the way, or it's not going to work. Okay, cos of 50 degrees, okay, times 10. All right, so that side, black X, is 6.43 meters. Now I'm going to keep all the decimals in my calculator. We talked about significant digits yesterday. I don't want to get rid of all those, but at the same time I'm too lazy to write them all. Okay, so I'm just going to write 6.43 here. And that is east. So what I just calculated is the horizontal component, how far east the object went in the first vector, in that 10-meter part of the trip. How would I find y? If I go back up to this diagram here, how do I calculate black y? Sine. Yeah, it's the opposite side. Right, so I would just do exactly the same thing, except instead of cos, I'll have sine. Sine of 50 degrees times the hypotenuse, 10 meters. All right, 7.66 meters. So, all right, so I just found the two sides of that triangle. Okay. Could I do the same thing for the red triangle? Definitely. I have exactly the same information. I have the hypotenuse, I have an angle within that triangle. I've got two parts of the triangle, I can find out everything else about it. All right, so if I want to find red x, x just happens to be adjacent again. X isn't always adjacent, it just happens to be in the two that I put on here. Okay, so x is adjacent, so I'll go cos of 30 degrees times 8 meters, okay, because my hypotenuse is 8 meters for this triangle. Okay, so I've got 6.93 meters. Okay, and that's also going east. Y is opposite the 30-degree angle, so I'll use sine to get it. Okay, and that's going to be 4 meters, and that one's going north. Okay. Did I just do trigonometry in my head? I did. But I cheated. I picked 30 degrees as an angle all the time because the sine of 30 is 0.5. So when you multiply by 0.5, it's just dividing by 2, makes me feel smart. So if you see 30-degree angles all the time, that's fine. All right, so now I know how far east each one of these things goes. I know how far north and south each one of these things goes. So if I go back to my diagram, black X and red X should make green X. It's not the colors thing, okay? It's just that they add together. Okay. All right, so red X and, whoops, that's not the line I want. Okay, so if I take red X and green X and put them together, that should give me green X. That is vector component addition. Okay, that's what we always do to solve vectors, is we add the X components together, we add the Y components together, and we get the total east-west, the total north-south. Right, so in this case, both red X and black X are east, so I can simply add them together. Okay, so green X will be 6.43 meters plus 6.93 meters. Now, I'm not going to use the rounded values. I'm going to use the full values in my calculator. Okay, and because I got this new emulator that allows me to grab numbers, it's so much easier. All right, so my total east, or total X component for the entire trip is 13.36 meters. East. Okay, so like I can go back up to my diagram and know that this line here is 13.36 meters east. Now, if I take black Y and red Y and add them together, do I get green Y? I do, as long as I recognize that one of them is south and one of them is north. Okay, it backtracks on itself in the vertical part. Okay, so I would have to make one of the directions negative. And that's the whole reason we do this. We break them down into horizontal and vertical, is so that we can have positives and negatives, okay, and make them essentially all collinear. It makes them easier to add together. So to get green Y, I'm going to take black Y, which is south, make it negative, and add it to my northerly one, which is 4. All right, so that should give me 3.44, right? -7. Oop. I got to take the whole thing. Okay, so I've got to have the full numbers here. And plus 4. All right, it's going to be 3.66 negative. It'll be 3.66 meters. Whoop, that should be in green. South. Okay, so now I know both sides of my overall displacements triangle. What can I do now?
To find the displacement, you would just do like a squared plus b squared plus c squared.
Exactly. I can use Pythagorean theorem to at least get the magnitude of my overall displacement, right? Because I know the two sides and I'm looking for the hypotenuse. So that would be my next step, okay? The displacement's overall magnitude is going to be 13.36 squared plus 3.66 squared. Okay, and again, I want to use all of my decimals when I do this. So we're going to have the square root of our answer. I'm going to take the, oop, I can't do that. I have to take the negative off of that. Okay, squared plus that one squared. That didn't work. Oh, I didn't put it in brackets. Okay. Sorry, keep messing this one up. Bracket first. Okay, then we can go on and get what I want. Without the negative. Squared and plus that one. Squared. Okay, so my overall displacement's going to be 13.85 meters. 13.848 actually. All right, so what else do I need? I now know how long D is. I need to know, I need to know the angle. Now, I know all three sides of that triangle. Can I use any trig function I want to get that angle? Absolutely. It doesn't matter which one I use at this point because I have all three sides. I just like tan best, so I'm going to use it. Okay, so I'm looking for this angle. That makes y opposite and x adjacent. Okay, so I'm going to go theta equals tan to the minus 1 of the opposite side, which was 3.66, okay, divided by 13.36. Again, we got to use all of our decimals when we do that calculation. So second tan without the negative. Divided by that one. right, so I'm getting an angle here of 15 degrees, 15.3 degrees. I'm going to go back up to my triangle here. Okay, my scale was probably not quite right. This probably wasn't 30 degrees here, which is why that angle looks a little more than 15 degrees. But is it still generally the right way? Okay, so if I'm looking back here at my diagram, this has got 2 significant digits, 2 significant digits, 2, so everything is 2. So how many can my answer have? 2. So now I'm going to go back and look at my numbers here. This to 2 significant digits is 14. This to 2 significant digits is 15. And I need a direction on that. Which way is that angle? Tess, which way is that angle? South of east. Okay, this angle would also be correct. Why? How can there be 2 correct answers? Right, they're complementary. Okay, they're complementary angles. If I'm looking at this diagram, I got this angle because I drew the triangle this way. There's nothing saying I could not have drawn the triangle this way. The sides would be the same size. The only difference would be when I calculated the angle, I'd have calculated that angle instead. And that would have been east of south, 75 degrees. Okay? Either way is fine. The reason I didn't draw it that way, I didn't want my lines going through the rest of my diagram. It gets really messy. So I tried not to do that. Okay? So all we have to do in order to do one of these, because I know this probably seems like really involved. It took us a really long time to do that. Okay? But in the end, I had to do some SOHCAHTOA. I had to do some adding and subtracting, and I had to do a Pythagorean theorem calculation. Okay? That's the extent of the math I had to do in there. None of that is terribly challenging. Are there a lot of nitpicky little steps and details? Absolutely. Okay? When you get good at one of these questions, probably take you 8 minutes, 10 minutes maybe, okay, something like that to do, just because there's so many steps. None of the steps are overly difficult, but there are a lot of them, and you have to remember which steps to do. On a unit exam, I would never give you one that had 2 angled vectors. Okay? I would give you one that had like a vertical and 1 angle. It's a lot less calculating because you only have 1 triangle. All right, so what we just did is all of the stuff I'm about to talk to you about. Okay? We have to be able to resolve a vector into its components. That is, find the x's and y's. That was the first thing we did after drawing the diagram. Okay? Was, all right, I got to find this side, so I'm going to go cos of theta times hypotenuse. I'm going to find this side, sine of theta times hypotenuse, okay, and go from there. That's how you resolve a vector into its components. Okay? You use trigonometry in order to find the sides. What we want to do is find the sides of all the parts so that we can put all the x's together and all the y's together because they're all collinear. Okay? And that means we can find the big picture. Okay? So if we were looking at this vector here, okay, if I wanted to find this side, it is adjacent to theta, okay, because theta is right here. Right? It touches this side, so this side is adjacent to theta, so I would go hypotenuse times the cos of theta. Okay? To get this side, it's opposite the angle, so I would go hypotenuse times the sine of theta in order to calculate that. Okay? Questions on the component part? All right, so if we were looking at this one here, okay, and the hypotenuse was 175 meters long, and we had this angle, 50 degrees, okay, to get x, I would use sine or cos. I know the hypotenuse is 175, and I know this angle, sine or cos for x? Cos, it's adjacent. Okay, I use sine for y, okay, and this would be cos of 50 degrees times 175, sine of 50 degrees times 175. Okay, and we have our sides. Okay, so the whole purpose of this, like we said, is to take our vectors. So if I had vector A and vector B, and I wanted to find their resultant, which is C, I would have to figure out how far over and how far up does A go. It's X and Y, right? How far over and how far up does B go? It's Y and X components. Okay, and as they're showing here, if I take blue X and green X, I would get red X. Okay, and if I took the two Y's, I would get red Y. Right, which is what we did mathematically. Does everyone understand that kind of graphically? Right, so that's what we did, okay, and that's the reasoning behind using vector components. Now, I know that some people yesterday who were at the end of class discussing the possibility of sine law and cosine law, okay, and I need to kind of put my foot down on that, okay, in terms of its usage. If you know how to use sine law and cosine law, they will absolutely get you the right answer. But that's all they'll do. Okay? And when we're doing vector analysis, we need to do more than just get the answer. Right? When we're analyzing vectors, we need to see within a trip, what is the object doing at each part of the trip? We need to break it down into the parts, and sine law and cosine law will not do that. Okay? We always look at everything from that vector perspective. When you get to physics 30 and you're doing conservation of momentum, it's even more so. You break it down into all the little bits, and cosine law and sine law don't do that. Okay, they're great for math, where the purpose of math is to get the answer. Okay, in physics, it's about understanding how you get there. Okay, that's kind of the difference between physics and math. Yeah. All right. I want you to write that one down and just draw the diagram. Okay, draw the vector diagram for that one. Give me a couple minutes and then I'll draw the diagram. let's look at just the diagram here at least. So my first vector is 235 meters east. Okay, and then my next vector is 400 meters at 30 degrees north of east. So in order to make sure I get this thing pointing the right direction, what I always do is draw a reference line in the second direction, because that's the direction this angle is measured from. So I just draw a dotted line that's due east, and then I go what I think is about 30 degrees north of that. I think my scale's okay, right? It's not, it's maybe about twice as long as that other one. It shouldn't be quite twice as long, but it's close. Okay, so this will be 400 meters. This angle here is 30 degrees. This line has an X and a Y component. Does the black line? Does the black line have an X and a Y?
It only has an X component.
Exactly. It only has an X component. I can't make a triangle out of a horizontal line. It goes east. That's it. It doesn't go north or south at all. So when I'm looking at this one, it's X, black X would be 235, and black Y would be 0, because it doesn't go vertically. All right, where would I draw a line that represents the total displacement? Ian, where would I put it?
From the start to the end.
Right, from the start to the end. So from here to there. Okay? Now, I can draw the triangle for this way, and it'll overlap everything, or I can draw it over here, doesn't really matter. I'm actually going to overlap everything on this one, just because I think it's clearer as to where I get my numbers from if I draw it that way. So there would be a green X, green Y, that angle. All right, I'm going to give you a few minutes to see if you can get that one figured out. Okay, your next step is to find your X's and Y's, and I already told you what your X's and Y's were for the black one. Okay. See if you can go from there. So the next step here is that we've got to find the x's and y's for our two contributing vectors. And as we already said, the x component for our first vector is 235 meters east. Eventually. There it is. Okay? So 235 meters east, and the y component for that is 0 meters because it doesn't go north or south at all. It's strictly horizontal. For our red vector, okay, we have to find x and y, okay, and it does do both. So x is adjacent to my 30-degree angle, so I'll have the cos of 30 times 400. Okay, so 346.41 meters east, and y is the opposite side, so that'll be the sine of 30 times 400, which will be 200 meters north. Okay. So now we've resolved all the vectors into their components. Okay, now you have to move on to what do I do with the components. Okay. So what do I do with the x's and the y's in order to help me get the big green triangle? Because what we're trying to find here is that overall displacement. So as I was saying earlier, like this is the kind of question I would give you on a unit exam because it's shorter. Okay? You still have to show me you can resolve a vector into its components. You still have to show me you understand you have to add the x's and y's and all of that. But because only one of the vectors actually has both an x and a y component, you don't have to do nearly as much trig. And calculating my resultance y is really easy because it's equal to what? Are these two sides the same? Okay, so that's another calculation. It's only an additional calculation, but it's one less calculation that you have to do. Okay, so if I'm calculating green x, that's going to be black x, or 235, plus red x. Okay, so I'll have 235 plus the 346.31, but I got to have all the decimals in here that were in my calculator, so I still actually have to do that addition operation. So I'll have that plus 235, so 581.41 meters east. And to calculate green y, well, green y is 0 plus 200 meters. Well, that's pretty easy. 200 meters north. Okay, because the black vector didn't have a y component. So now I've got the two sides of my overall triangle. So now I can go to Pythagorean theorem and get the magnitude. So 581 squared plus 200 squared. And again, I keep harping on this, but I'm going to keep harping on it. I'm going to keep all the decimals. I'm actually going to use them all in my calculator, okay, because that's really important. So square root of, okay, that number squared plus 200 squared is going to give me 614.85. meters, and I don't have a direction on that yet. That's the next thing I have to calculate. So now I know how big d is, but now I need to calculate what theta is. All right, I'm going to use tan, but at this point I could use any of the trig functions because I have all three sides of the triangle now. All right, for me that's going to be the opposite side, which is y, divided by the adjacent side, which is x. Second tan of 200 divided by that one. All right, so I'm getting 18.98 degrees. Which direction is that 18.98 degrees? Josh, which way is it? other way. North of east, right, because the angle arc is touching east and going north of it. So whatever direction the arc touches, that's the second direction. It'll be of that direction. So this is north of east. Last thing I gotta check, significant digits. Okay, 3, 3, 2. The angle is a measured value. Okay, because it's a measured value, it does in fact contribute to your significant digits because obviously you used it to calculate quite a few things in the course of the question. So my final answer then will be 6.1 times 10 to the 2 meters at 19 degrees north of east, or I can also write at 71 degrees east of north. Either one of those would be correct. Okay, does everyone understand the scientific notation that I used? Okay, you're going to have to use that a lot when we're using significant digits. Okay, so you're going to get numbers that are big, and you're going to have to put them into scientific notation. Now, something that I am seeing, I'm not sure where you guys are getting it from, but someone's showing it to you. Proper scientific notation, the base number, in this case 6.1, is always between 1 and 9.9. Okay? It is never bigger than 10. Because I'm seeing, like over the last couple of years, I've had people who are telling me that this answer is 61 times 10 to the 1. And while mathematically 6.1 times 10 to the 2 and 61 times 10 to the 1 are the same number, that's not scientific notation. Okay, proper scientific notation, the base number is between 1 and 9.9. All right, how are we feeling about that? Okay. Like I said, for like as long as you have been alive, every unit exam for this unit, I have given a question like that. Okay, one line that's either horizontal or vertical, and one line that is angled, find the total. Okay. I want you guys to see if you can draw that one. On this one, scale is important. Okay? If you recall, I told you the toughest part of this, the part people screw up most often, is the picture. So it's really important that we draw the picture correctly. So see if you can get the correct diagram here. I'll give you 3-4 minutes and then I'll draw it. Okay, so for our first vector, okay, they're telling us that it is 70 degrees above the horizontal. So what I do is I draw a line that's horizontal. That's where it's measured from. And then I go 70 degrees above that. So I guess something like that. Right, so drew that a little long. I'll make that 70 degrees. This will be 145 meters. This will be X, and that will be Y. All right, and then my next vector, they tell me is 105 meters long, so it's going to be a little shorter than that one, and it's 35 degrees below the horizontal. So once again, I draw a reference line that's horizontal, and then I go 35 degrees below that. That's a little bit long. Okay, so those would be my two vectors. Okay, 105 degrees, 105 meters, 35 degrees below the horizontal, and 145 meters, 70 degrees above the horizontal. Now I still have to draw my overall displacement or my resultant line on there. What's that going to look like? All right, where's it going to go? Right, from the initial position to the final position. So it's going to look like this. Okay, so I'll be looking for that angle. I'll be looking for that side, and I'll need this side and that side. Okay, that's some job. Alright, I'll leave you to it. You gotta calculate some x's and y's now. Here. Okay, so the next step is we gotta find all of our x's and y's. So blue x on this diagram is the adjacent side to the 70-degree angle. So that's gonna mean cos of 70 times 145. Okay, so that's 49.59. Meters, and that is not east, but it's positive because they tell us it's horizontal and vertical. Okay, so that's the positive x-axis going that way. Right? And then our y component is the opposite side, so sine of 70 times 145. And it gives us 136.255. Meters, and that's also going to be positive because it's up. Okay. And I got to do the same thing with my green triangle. X just happens to be the adjacent side again, so it'll be cos of 35 times 105 this time because our hypotenuse is only 105. So cos 35 times 105 is 86.01 meters, and that is positive because it's that way. Okay, and our y is the opposite side, so sine of 35 times 105 and it's 60.22, but it's negative because it's down. Okay, it's going this way. All right, so now I've got all my x's and y's. Can I find my big triangle? Okay, so that's my next step. Okay, looking for the big triangle. So both x components go to the right. They're both positive, so all I have to do is add them together. 49.59 plus 86.01. I have to do that with all the decimals. So that one plus that one. 135.6 meters, and that's positive. Okay, and our y component, we've got 136.255, that's blue y, and we've got negative 60.22 for green y. So that minus that, 76.03 meters, and it's still positive because it's still above where we started. Are they all right so far? All right, what's my next step? Jordan, what's my next step?
I don't know.
All right, I got this side and this side. I'm looking for that. How do I do it?
Pythagorean.
Diagram theorem. Okay, so D will equal 135 squared plus 76 squared. Again, putting all the numbers into my calculator when I do this. 135 there. Squared plus that one squared. All right, 155 meters, 155.46 meters. Okay, and then the last thing I have to find is theta. Okay, I'm going to use y and x to get that, so opposite and adjacent. So that'll be theta equals tan to the minus 1 of y, which was 76, over x, which was 135. Again, using all the decimals. Whoops, 76 divided by 135. 29.28 degrees. Okay, and how many significant digits do I have here? 3. Everything's a 3, right? 145 has 3, 70.0 has 3, 105 has 3, 35.0 has 3. Okay, so my final answer is going to have 3 significant digits, so that's going to be 155 meters at 29.3 degrees. And then the direction for this one would be above positive x axis, because that's all they told me. Okay, everything was in reference to the horizontal.
How did you get 76 for your y?
So to get 76 for my y, I took this side here, which was 136, and I subtracted this because they backtracked, right? This one went up and this one went down. So I'm at 136 minus 60. Yeah? Like I'm adding them, but I need one of them negative. Yeah, is that right? What were you getting?
I got 50.34.
Must have just typed something in wrong. Yeah. Okay, is there a possible second angle that would be acceptable there? I could have the complementary angle to 29.3, so 60.7 degrees, okay? And that would be right of the y, positive y-axis, which would be a really weird way to say it, but you could do it. All right, how are we feeling about those? Right now they're slow and tedious. Later they'll be faster and tedious. Like, you won't promise the tedious part goes away, because it doesn't, but you'll get better at it and you'll be able to go faster. Right? Again, there's nothing here that's like really mathematically challenging, but there's a lot of stuff to do and a lot of steps to remember. The good news is the steps are always the same. Draw the diagram. Find the x's and y's. Add the x's, add the y's. Pythagoras, trig, done. Okay? It's always the same steps. So once you learn the steps, you can apply them to any vector addition question. All right, I want to look at another type of vector question that we haven't gone over yet, but it's kind of related to this stuff. So, okay, we call these boat questions. They usually involve a boat. We try and keep it simple. So let's say this is a river, and the river is 50 meters across. Let's say that I can row my boat at an Olympic caliber 3 meters per second. Okay, that's like fast to row a boat. Right, so I'm going to row it, but I'm going to row across the river. So I'm going to point the boat that way. Am I going to end up going that way? What's going to happen? I'm going to go kind of diagonally, right, because of the current. Okay, so let's say that this river's current is 1.9 meters per second. So I've still drawn these two vector quantities tail to head, but they're not displacement vectors anymore. Now they're velocity. Does it change what I do? Doesn't change it at all. All vector quantities are added in the same way, tail to head. Okay, so it doesn't matter that these are now meters per second. So if I was to do what I've been doing, okay, would I be able to calculate the resultant velocity as I row across the river? Okay, and if I had like a drone or something above me while I'm doing this, it would look like that. Right? I would move diagonally across the river, even though I'm not rowing that way. I'm rowing straight across. But the river current pushes on me while I row straight across, and I end up going across along this diagonal vector. Right? Would it be pretty easy to find the resultant velocity and its vector. Okay, that's the stuff we were working on yesterday. It's just perpendicular vectors. And so that would be pretty straightforward, pretty easy to do. Here's where this question would become a little bit more involved. How far downstream will I be when I get to the other side? I want to figure out how far downstream I'll be when I get to the other side. And I'll tell you this, you won't use the green stuff at all, and you won't use any trig to arrive at this answer. All you will use is this number, and that number. And one other number that you'll calculate. So when I'm doing this, when I'm rowing across the river, how fast am I going across the river?
3 meters per second north or forward.
Yeah, forward. 3 meters per second this way, across the river. That's how fast I'm going across the river. It's 3 meters per second. How far across the river? 50 meters. Can I figure out how long it'll take me to get across the river? Okay, this is what we have to understand. Even though there's a current here, that current does not affect how fast I row. I'm still crossing the river at 3 meters per second. I'm just not going to end up straight across the river. Okay, but I'll cross the river in the same amount of time that I would cross a lake that's 50 meters wide. The only difference is I'd get straight across the lake, but it would take me just as long to get across. So if I want to calculate the time, that's d over v. 50 meters over 3, I think that comes out to like 16.6 repeating, right? So it's going to take me just over 16 seconds to get across the river. All 16 seconds, I'm not just going across, I'm also going with the current downstream. How fast am I going downstream? 1.9 meters per second. Okay, so if I know that, if I know how fast I'm going, and I know how long I'm going to go that fast, I can figure out how far downstream I'll be. These two things are happening concurrently, okay, at the same time. So the time is the same for both of them. So I take my 1.9 times, 16.6, and I think I get 32 there, right? 32 meters after you round. 32 meters downstream. Okay, so this is, if you recall, I discouraged the whole cosine law, sine law thing. This is why. Okay, sine law, cosine law could have got an answer for like the hypotenuse of that triangle, but it couldn't have done this one. That requires us to look at the pieces, to analyze the individual vectors. Okay, so we'll be looking at some boat questions tomorrow, including ones where you have to change your heading because you row into the current a little bit. Okay, it's still simple vector addition stuff, not as complex as what we did today, but it's still analysis of vectors. All right, get you guys to mask up and pack up so I can come around and wipe down those desks.